Okay, hi everyone. Welcome to Mission Control 3. So today we have a treat. We have Dr. Tam coming from SOC. He's a postdoctoral fellow here. He's working on many different areas. But today he's decided to help us out and give us an introduction to databases. I think you all have some understanding of what databases are, but it's a time to get a little bit more of a refresher and to look at the underpinnings, because what you're using in data store right now, if you're doing the Vostok level and using Google App Engine, you have some exposure to what data is and how to organize it, but you can see a little bit of how the structure of it works. Okay. Other announcements are because we are going through the evaluation phase. Hopefully, everyone in this room has put up their project log and README. Is that right? Okay. Please make sure you've already tagged it correctly to the visibility of your evaluation group. And over this week until June 9th, next Monday, you have to do the evaluation of 3 peer groups. Okay. So if your peer groups that you find on Piazza have not posted a project README and log, you're not responsible for evaluating them, because some people have dropped out or weren't able to complete on time. So in those cases, you're excused from that. Okay, if you're not sure, because Piazza is a bit hard to use, it's not easy to find things in Piazza, even with the search function, then you can write your your advisor, okay, ask for some input. They will also be trying to remind you about deadlines for this, okay? If you have any questions, again, there are the posts on Piazza. You can give us a follow-up, then we'll know that there are questions, and then we can go on. So today we have Tom talking on databases, so I'm going to hand it over to him. So all yours.
Thank you for the introduction. Have you stopped the recording?
Yeah, it's recording already. Let me just double check on that. Yeah.
Okay. 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 Hi everybody. It's nice to be with you in this mission control. And in this talk, first we're going to review a little bit on the Google Data Store that you have learned in the previous lift off section, and then we will discuss on other benefit of database beyond the Google Data Store, and after that we will have some hands-on exercise on how to design a database for a web application, and we also have a chance to write and execute some SQL statement. And finally, if we have time, I think we will discuss a little bit on the advantage of SQL and NoSQL, and in which case we should use either of them or a combination of them. Okay. So I think that you have managed to build this application in the list of section, right? So in this application, it mainly record a list of items that a person would like to have, right? And all these information is recorded into the data store. So basically, Google App Engine use a key value and hierarchical data model. Is it called key value? Because why? Because an entity or an instance of a class, it should always be identified by a key first, and then is it attached by various attributes or values. And beyond that, is it hierarchical because all the data related to an entity will be clustered, will be grouped together with the parent entity. So even though this data model provides some benefit, for example, um, scalability and fast read, because all the data related to a user, to a person, are clustered together. Yeah. So it will be very efficient for the read operation. But as we will see later, it will need to pay different trade-off actually. And I think roughly I have reminded you a little bit on the consistency issue regarding to using Google Data Store. For example, in your application, you need to be very careful, and if you would like to see the consistent data after an update, you need to use the keyword. You need to query with the ancestor keywords. Otherwise, you may see some inconsistent result. Okay. So besides this disadvantage, the key value model may have other problems also. For example, data redundancy. Why? Because you know, now you just think of a situation where two people can would like to have the same item, right? But in this model, you need to predicate the item information into two clusters. One is for the first version, and also that information for that item need to be predicated in the second version, and so on if you have multiple people that would like to have the same item. So that means you need to replicate all those data. And one of the consequences of that is the expensive cost for write, right? Because you need to write multiple times, right? If you would like to update the information of an item, for example here, like if the user just have some typo on the name of the item, right? You need to modify it, so you need to update the information across on the data on the cluster. Okay, and another drawback is that actually the key value and hierarchical models, it can provide, it can be only useful for a limited application scenarios, and in fact, not on database application can be really fit into this key value model. So let's see the other widespread application of database. For example, social networking application is actually one typical app that is backed by database. So I think you may want to have a look at these two blocks to see why Facebook use MySQL for its timeline, and you will be also interested on how they can really make the MySQL database to be scalable, similar to the capability of Google Data Store. And you may also know about NUS Live. This is actually another social networking that was built for NUS. It was first developed by a group of graduate students in database research group, and they also used MySQL as the backend data store for this application. Okay. And online games, for example, are other applications that also need the backend database, for example, to maintain the score of within user. And also at NUS, the staff portal and even for the student portal, these enterprise application either provided by SAP or Oracle PupilShop. So both of these applications again are also backed by the underlying database. Yeah, yeah. So this is just an introduction on the widespread application of database. Okay, and now let's go through the main content of this mission control, which is about how to design a database. Actually, the designing is important because it ensures that the final software, or for your case, the final project, meets the requirement. And here we only focus on a data requirement for the application. And actually, the designing of a database includes 4 major steps. First, we need to create a conceptual design. Then, secondly, we need to select which DBMS software that we are going to use. After that, we need to create a logical design from the conceptual design. And finally, we need to determine the physical design for the database. So now I will go through each step. And after that, we will have a hands-on exercise with this. So in the first step, conceptual design. So basically, data modeling means we are going to create a very abstract data structure to represent the real-world application. And in this step, we need to analyze the data requirement, and then secondly, we need to model those requirements into a higher level abstract using a diagram called entity relationship diagram. And the last sub-step is optional, where we have some final verification on the model. So the purpose of the first step is to collect all the information needed by the application. So in this step, we mainly have some interview with the real user, or maybe we pass them some survey for them to fill in, so that we understand what the user would like, what information they would like to maintain in the application, for example. And this is, for example, a result, a data requirement after those interviewing and survey. For example, I think I will let you 1 or 2 minutes to have a look at this data requirement. This requirements is for a database backed by a retailer. This will be quite similar to the exercise that you were doing also. Okay. So I believe you may think that this data requirements is quite a little bit long or wordy, right? So actually, this requirement can be captured by this very concise diagram. Okay. Um, and let's see how can we do this. Um, so there are several components in an ERD, which means entity relationship diagram. First is entity type. And entity type means a collection of uh, of some type of things. For example, a collection of people, a collection of objects or places, um, and for which for this entity type, we need to record on the data or information related to this. Okay. So basically, entity type means a set of things or people. So for example, from this requirement, right, we can identify several, actually 5 entity type, which is cities, right? And we have stores, items, customer, or orders. Basically, they are all the common nouns in this requirement, right? They are entity type because they mainly a set of the things that we need to capture the information. For example, for the store, we need to record the information like the store ID, the address, or the manager ID, right? Okay. The second component of an ERD is relationship type, which means the interaction between entity. For example, here we can see a city may have several stores. So we have the relationship between a city and a store. Okay. So that means we can identify a relationship between them. Okay. And the third one that we need to consider is cardinality, which means the maximum number of times that an instance can be associated with the instances of the other entity type. Okay, let's see an example here. The cardinality is denoted as either an integer number. For example, in this case, it's 1. That means one city will involve in this relationship, while in the other end, and here means multiple stores could be located for a given city. Okay, so here 1 or n are called cardinality, means the maximum number that an instance of entity here could involve in the relationship. Okay. And the last component is modality. Is just on the contrary of the cardinality, which only means is it the minimum number of an instance that could be involved in the relationship. So, for example, here, given an order can only exist if it contains some item, right? We cannot have some order from a customer that have no item in the order. So that means the minimum number of item involved in this relationship should be 1. Okay, so this concept is called modality, but in this notation we did not record it. Actually, in other notation of ERD, for example, here, if we have a circle like this, so that the modality means optional, meaning that this entity could involve or not. Yeah, but at the other end, if there will be a straight line like this, it means that this entity should exist in the relationship. Okay, but because currently in this example I'm using this notation, so it mainly does not have short concept. Okay, so actually there are a wide range of notation for ERD. So actually you can choose either of them for your own, but normally we will use the one that are commonly used in your organization, in your workplace, for example, or when you study at NUS. Actually, in level 2 database courses, we actually introduce another notation different from this, and during the exam you need to follow that notation. Okay, and now the problem is how we can identify all these entity type, relationship type, or their related attributes. Okay, so this is just a guiding principle. It's not always true, but we can use this principle to identify these component of an ERD. So you may have noticed that I have different color for this component. In this case, the common nouns color in red, they will be entities, right? And on this verb in the blue color will be the relationship type. Okay, and after we have identified all those entity type and relationship type, the other related information are just their attributes. Okay, and the last step in The last sub-step in conceptual design is we just verify again in case we miss some additional we miss some entity or attribute details, we need to identify some potential security breach, for example. And after the conceptual design step, we come to the second step, which is to select which DBMS software to use for our project. So here are several factors that we need to consider. For example, the license cost or the features that the DBMS provides, and all the factors like the DBMS hardware requirement, because it may eventually add up to the total cost of owner. But however, unless we have a very special application, otherwise I think in each industry we almost have several typical use case for each industry. For example, if you are developing an e-commerce app, it's more likely that you will use the open source MySQL database, which is freely integrated with the WAM server or the LAMP server. Yeah. And for enterprise application, it's mainly you will use like the Oracle database or the Sybase of SAP, for example. However, just to give you an example, let's see in which situation we should use SQLite, which is the DBMS that we are going to have on hands-on today, and in which situation that we should use another DBMS. Okay, so the information is given in this link. Let's go through it. Okay. So the main use case for SQLite is mainly for single user, and is mainly embedded in the application. There's no separate project of SQLite. However, if you are going to develop like web application using the client server model to support like 1,000 or 100,000 of users with a high degree of concurrency, yeah, so SQLite will be not able to support this. Okay, yeah. So this is an example on how you consider which DBMS to use, yeah, from both technical perspective and economical perspective also. Okay, and the third step, which is also important, is that we need to translate the initial conceptual model in the graphic diagram, right, to a structure of database. Normally, it will be a relational schema. So in the ERG, we mainly have two main components, right? One is the entity type, and the other is relationship type. So now let's see how we transfer them into the corresponding tables in our database. So for an entity type, we will create a table or a relation with the names is similar to the name of the entity type, and this table or relation will have the columns corresponding to X attribute of the entity type, and there will be a primary key for this table. Okay, so the primary key is basically the attribute that identify the entity of this identity type. For example, given our previous ERD, right, we have an entity type called city. So here in this logical design, we have a table, or here we call a schema or relation called cities, and it includes several attributes or columns: city name, state, headquarter addresses, which are all the attributes attached to this entity type. Okay, so transforming entity to table is quite simple, right? But now we need to deal with translating relationship. So actually, we have two main types of relationship. First, the one-to-many relationship. To translate it into a table, actually, we only need to define a foreign key on the many size, referring back to the primary key of the one side table. What does it mean? For example, here, okay, this is one-to-many relationship, right? One city have multiple stores. Okay, so to translate this relationship, we just add two additional attributes, which is city name and state from this entity to this entity. Okay, so these attributes are colored red here. So that means given a store, beside its original attribute, we need to add in further information, including the city name and the state, so that we can identify which city it is located. Okay, so that means in this table there could be multiple stores that have the same city name and state, right? Okay, that's the way how we translate the one-to-many relationship. Okay. Now, for many-to-many relationship, actually we are going to create a totally new table, and that table will first include all the key that reference back to the other entity. and plus on its existing attribute. For example, here we have, okay, this many-to-many relationship to express that one order may contain multiple items, and at the same time one item may belong to different order at different time, right? The only difference is only the quantity. So in different order, the specific quantity related to an item could be different. Okay, so for this relationship type, we will create a separate table called item order, and it will have two attributes, which is order number and item ID. Actually, they are called foreign key. It will refer back to the order number of the order and also refer back to the corresponding item ID of the item here. And beyond that, we need to include the quantity of this item in the order also. Okay, so those are the basic steps that how we can translate a diagram into a relational schema like this. Okay, and the final step of database design is basically to map on those objects like the tables, the attribute into a specific DBMS object. For example, we need to determine the data type for its attribute, whether it's an integer or a double value, or whether it could be a fixed string or a variable string. That is the basic step. Beyond that, we may need to define some index or view to speed up query processing, for example. But I think those design choice are quite advanced, and you may only need it in the future, but not in this project for Orbital. Okay, so that's a very brief introduction on database design, on how to collect the data requirement and how to abstract it into a high-level diagram and to translate into a relational database model. Okay, so I think now it's time for us to do some exercise. First, we would like to design this database, and later we will try to populate this database into a real DBMS and try to perform some query over it. Okay, now let's start. I think first you just have a look on this data requirement. Then maybe one of you will try to draw an ERD for this. Okay. Actually, this is quite a little bit simplification of the real inventory database for fair price retailer, for example.
So tell them what you want them to do.
Maybe you can try to draw the diagram on your own notebook, and maybe one of them will draw the diagram on the whiteboard here.
Okay.
Yeah.
Everyone, if you have a sheet of paper with you, maybe you can pull out a sheet of paper and try to work through constructing an ER diagram, just as Thomas showed you in the earlier example. You know, where you have the rows in the table as well as the relationship joined by a diamond. Does anyone need paper? I can run and get some paper. Okay. I'll be right back.
But actually, they can draw in their Word document or their Microsoft Word.
Okay, if you have PowerPoint, you can try there. But if you want paper, I'll be right back. It's sometimes easier to do it.
Yeah. But first, I will show you again the notation. For example, here, an entity will be rectangular with the entity name together with all its attributes, and normally the identifier attribute will be underlined. Okay, and and this is the relationship, and you need to add the cardinality also. And a relationship may contain attributes also. Okay. Actually, I think this step is quite important. Even you use Google Data Store, you need at least to model your data requirement so that you can identify uh, what is the main entity, for example, and what will be the child entity. Yeah.
If you're on the slides, you can also flip back to the page where has drawn the ER diagram for the preceding problems, and they give you some hints about the relationships between the different entities that you're putting into the tables. So just like Tom did, you might want to underline or color or highlight, you know, the different verbs and nouns that tell you the relationship between the statements. So treat this also as a preview of a course to come. You know, Tom alluded to the fact that databases is a key course within NUS. It's not a core requirement, but it is for many focus areas something that you should learn. It's a pretty central statement for computer scientists to say that they know what a database is and how to design a database, right? Just like you couldn't get out of computer science or information systems without saying you've done some sort of programming before. I just have to do databases. Okay. It's actually have a harder requirement than our CS colleagues. This paper here, you need paper?
Right. Right on the whiteboard. Yeah. I think what is like correct is just to translate here, right? You just like call it inventory on the home of okay, information or many consider what we need to extract the key consider and we also see the data together so for this product for how many items of this product you have
Yeah, if you finish the exercise, you can also think about your particular application. I think a lot of you are doing that as well. You know, if I was doing my orbital project, what type of data, what type of tables, what type of relationships do I need? And you can start designing that with your partner if you haven't already done that.
you have this entity one I think this is one many like we try to assume that different from you have the same product ID. So yeah, so the same product ID different store may have different watch. Yeah, yeah. No, but my argument is like this, right? Given a product ID, right? It could be available at different store, right? With different number, different quantity. So this would be many.
Yeah, right, yeah.
Because it's not mainly here, right? For your case, you may not able to support the case where the product, the same product, you have different quantity at different stock. But here you, for your case, different store has different source ID. It's not a consistent product across all the. Yeah, I think most of you have used a try, so I think let's have a look at the answer. So actually, we have a very simple ERD. So for this retailer, we have multiple stores across Singapore, right? And in each store, there could be different type of products and their corresponding quantity. Okay. So this is a many-to-many relationship. Actually, okay. One of your friends actually have another interesting solution, which is that actually this relationship can be modeled as an entity. We call it inventory entry, for example. And then we have a one-to-many relationship to this entity, and the same for this direction also, one-to-many relationship to this entity. Yeah. Anyway, it's just a way we represent a many-to-many relationship. Yeah, it can replace by an entity. Okay.
Can you explain why you would do that? So you're saying something like this, right? So you're going to replace it with another entity table, right? In
Yes.
inventory, and then have a many-to-many relationship between the store and the inventory, and another many-to-many relationship between the product.
Okay.
Right?
I think
Is that correct?
the cardinality here, okay, should be one store could have multiple entity, but the other only one. So well, it's about where we place the cardinality. I think, yeah, this is correct. One in here and n in here. Okay.
Okay.
Yeah. And in the other direction also. One. Yeah. Two n. Okay. So in this way, we means that one store could have multiple inventory entry, right? So that means in this table we have multiple rows corresponding to a single store. Okay, and similar for the product ID. Yeah. So actually, the resulted schema should be the same, right? Because we try to translate two diagrams into the schema, right? You will see the same result. First, if it is a many-to-many relationship, right? So the inventory table, it should include the primary key from both related entity type, right? And in the other ways, if you consider this as an entity type, right? So for this one-to-many relationship, we need to add the Boston code primary key to this entity, and additionally, because it have another relationship one to n also, right? So we need to add the additional ID here to the attribute list here also. So either way is fine. Yeah. It's just how we design, how you are comfortable with which design choice. The result the schema will be the same. Okay, so that is how we design a database given a database requirements. Now we have several hands-on exercise. First, we will play with SQLite, right? Then we try to populate a database and perform some SQL command. For this exercise, I think you can refer to my step-by-step document here. Just follow this link. Yeah, just follow this link, and this is the instruction. Okay. First, please try to download the tool SQLite tool here. For Windows, you will basically you will download the SQLite shell for Win32. Okay. And we also have a version for Mac OS also. So just try to download the appropriate version for you. The downloaded file should be a zip, so need to unzip it into your designing directory, your preferred directory. And actually, we do not need to install this application. Yeah, we just launch it from the execution file. Okay, thank you. So this is the command line interface, yeah, of SQLite, where we can input the command. Okay, so let's start. You may have noticed the message here. For the first time we launched the application, it mentioned that the database is just in memory. That means for whatever we update to the database, it will be lost if you close the application. So actually, the very first step is to reopen or to create a new database that will be persisted onto the disk. So with this command, open, okay, and follow it will be the file name or probably with directory. So with this command, all your data will be persisted to this file, okay. And then you can try this very basic SQL statement, okay. First we try to create a table including two columns, right? ID and value, and their data type is a string, a fixed string, and a small integer. Okay. Then we try to insert two tuples or two records into the database, and finally we list out all the record in the table. Okay. So we have just created the table. Inserted the first record, and then we see okay, our first record has been inserted. So actually, SQL or structured query language is the language where we can access and manipulate a database. So for example, here we create a table. All these are keywords, and then the table name, and all these on each column. So actually, at the end of this document, I will provide you the resources where you can learn more about Cisco. Okay, so if you are done with it, we can move to the next exercise where we will populate a sample data. First, try to download the data from here. Okay, so in the directory, after you have unzipped the downloaded file, you will see several SQL script. Okay. For example, if you want to have a look, correct SQL. Okay, correct.sql. Here, actually, it contains three statements. The first, it will correct the product table. The second, correct the stock table. And the last one, the inventory table. Here, you see, besides all the attributes that we have designed in the logical schema, right? Now we need to determine the data type for each attribute. Yeah. This step is called physical design. And primary keys mean is the primary attribute for each entity. And for a table, it may contain some foreign key. As I mentioned, this attribute will refer back to the, for example, for the Boston code here, it will refer back to the Boston code of a store to represent the fact that this inventory entry is for this store. Okay, the quantity of this product is for the corresponding store. Okay. So actually, on those scripts was prepared for you already. So you only need to execute the entire file in the SQLite command line. Yeah. So you just follow the step provided here. First, correct the table, then the subsequent SQL file, if you have a look into it, actually it contains all the insert statement to upload all the data, to populate all the data into the table. Yeah, if you are interested, you can have a look later. I think we need to define the exact directory. Yeah, for Mac it does not. It have different default directory. we um, we just use the full directory here. Yeah, yeah. Because I think for this version, the Mac version is not working well with the default directory. Okay.
Big file.
Not big, but I think we have some typo here, so maybe it's hang or something. Ah, okay. Actually, we have some other command, for example, tables to list on the table that we have created. Okay. And now we would, for example, would like to see on the data from the store table. Okay. So after you have successfully populated the data here, please just try on this example query. Okay. Actually, I have provided you the answer already. So the first two queries it mainly access a single table only, the store, because we only need the information of a store. Okay. The first one we just list all the data. While the second one we have some filter condition from this store, but then we would like to restrict where the area of the store should be plenty. So this is an example of how we query our data in a table and properly with some constraint or some conditional predicate. Actually, I think there for SQL there should be a lecture for that also. So I think in this tutorial I just provide you some example, but I'm not going to much detail. And when you need it, I think you should be able to learn yourself. And the third query, it could be interesting because even though we also would like to access the same table store, but in this case we need to do something called self join. So if we look at the requirement, we need to find the script where there are more than one store. Okay, so that means if there are two stores that is not allocated on the same street, right? So it is expressed by this filter condition here. Then we need to ensure they have different Boston code. So in this case, it means we have two stores, right? Two Boston code means two stores. Because Boston code is the primary key of the table. For the fork query, we would like to list all the addresses of the store keeping more than 800 jars of this butter. So even though the requirement requires short, right? But actually the query is quite complicated, and we need to retrieve the information from all the tables in our database from the product. Because why? Because we need to have a filter condition on the name, right? And from the inventory table, because we would like to check the quantity, and now we would like to retrieve the address of the corresponding store. So that means we need to join all these three tables together, and we have some additional filter condition. Okay. So typically for subquery that retrieve the data from multiple tables, we usually have a join condition where we require that the attribute from one table equal to the corresponding attribute from another table. We call this a join condition. This is actually related to the foreign key that we have defined before. Yeah. But this difficult to retype.
Yeah.
Format.
Yeah.
Yeah.
And I can retype. No, it was these nice control characters.
You got the result? Yeah. That's it. We can open the MC. We have a doc.
Is that one?
Yeah, let's try and let's see. Yeah, it should be like this. Okay. Okay, never mind for the last query. We have some additional clause where we would like to order the result based on some column, and further in the projection clause we may even have some simple computation, right? We would like to compute the total value of on the product. Yeah. So actually we have some formula here, and sometimes we may we do not need to have a very exact match for an attribute. In this case, we have some filter like this. Okay. Okay, I think that's all for the hands-on exercise. I think you can try out more at home later. Let me think. Okay. So you have learned how to design and how to play with some DBMS, right? So now the next question is how we how a web application can retrieve the data from such database. Because recently you just use some command line, right? But your main purpose eventually is how your web app can retrieve data from database and not from the command line. So this is an example. We have the user can input some search condition and the website will perform some query. Actually here it just have a select query with a condition, with a filter condition where the book titles is something like the database keyword here, and given on the result returned by the database, the website will render on the result in a table like this. So how to do this? Actually, in this example, I use PSP and Oracle. Actually, you can email to the instructor if you would like. Okay. Actually, our school provide a joint account where you can deploy your website, and you can also apply for an Oracle account also where you can store database over there. You do not need to install your own Oracle instance. And to apply for this, I think you might need email to the instructor to get the permission from the school.
So you can go to this post if you'd like to get your own server. Basically, you can apply within the eForm service to get your own server here. So you have to put in your details here. Just show you for the sake of it. Okay, so you have to apply for, I think, not really sure which one it is. I think it's computing resource. If I'm not wrong. No. Yeah, and you have to select here something like a virtual machine.
Yeah.
So one of those things down here. And then you can do that. And the Oracle account is also.
Okay. Okay, that's one way that you can use a server script to access a database. But actually, I think you are familiar with Python, right? So actually, SQLite is also integrated with Python already. So you can follow this tutorial to see how to access and manipulate data from Python. I think you can give it a try later. Okay, so now that we have learned about SQL, right, and also NoSQL in the previous lift up section. So actually, each type of data store have its own advantages. So it depends on our application, so that we choose which type of data store to use. Actually, in last year, I presented a mission control about this topic. It's quite long actually, so here I will just give an overview, and if you are interested, you can follow this video for this topic. So I just go very quickly on this, the comparison between these two types of data store. So SQL database are better for providing strong consistency and a wider range of query capability. On the contrary, NoSQL, for example, Google Data Store, it is more scalable, but you see, it's also limited to some application scenario only. So actually, the best solution in this case will be a hybrid that combine the advantages of both approaches. So how can we do that? Let me show you. So actually, in our application, right, we can either have different portion of the code that access different type of, whether it is Google Data Store or it is the Cloud SQL. And we only need to classify the data into different types. For example, in this application, we will, in this track list application, the user mainly post on the advertisement onto this website, right? So underlyingly, the application will mainly maintain all the active, all the new listing inserted by the user on a SQL instance, so that it could be it could have a strong, consistent, and all the advantage of the SQL also. And after a while, we will move on those data that become quite old or obsolete into a bigger Google Data Store. Then that means you can reorganize the table into the hierarchical model so that it can support more efficient query for the parent and the child relationship, for example. So that means within one application space, so sometimes you will access the data in the SQL instance, and sometimes you need to retrieve the data from the other data store. That's the way you combine the advantages of both types of the database. Okay. So if you are interested in this topic, just watch the video that I presented last year about, actually I presented more about the trend that lead to those emerging NoSQL database, for example, the cloud computing model. And then I also discussed multiple typical use case for NoSQL also. Okay, I think that's all for today mission control. I hope you find this is useful and helpful.
So Sam has also posted in his notes some technical terminology. You should all be pretty familiar with what that means by now. Okay, and especially the resources for understanding SQLite better. For example, when it works well, when it doesn't work well, we went over that today. And there's a homework for mission control. As you know, if you do enough of the homeworks, 2 or 3 of them, they qualify you to do Project Gemini or Apollo 11. So you can use that in your documentation to convince your peers that you've done enough for those advanced levels of achievement. So if you can do this, it's not that hard. It's to design a database for patient appointments. You can try to translate these into an ER diagram, 1 or 2 of these. If you can do them all, that's great. And then you can either take a screenshot or a picture of your piece of paper and post it as a follow-up to the mission control here, right? So you see the post that we have about this. So you can just go post a follow-up here. So, any questions for Tom? Okay, I think we went over SQLite really nicely. You know, you guys got the basics of how it works, and I hope you were able to complete some of the exercises together. So let's thank Tom for all his hard work.
Thank you.
So next week there will be another mission control 4 on introduction to security, which is a really hot topic these days, given how much of it we have seen problems with in the Singapore government, if not Heartbleed or other things of that sort. And it will be done again by an external sponsor. However, it will be on Monday night, so it will be on 9th of June, and it will be here, I think, in SR3 or SR2. Let me just double check that so that I don't give you the wrong information. So it'll be here in SR3, and it's run by these nice folks who have volunteered their time to come and give us a presentation. So they charge for these types of sessions for people in industry, but you're all students, so you get it for free. Isn't that nice? Okay, with the expense of your time, of course. Okay, so we have the classroom until 9, so you're welcome to stay and work with your partner and talk about your things. So with that, we'll finish the recording.